All right, let's take a look at polar coordinates and polar graphs. First, let me give you a basic idea of what we're talking about with polar. If we are in the polar coordinate system, instead of the Cartesian or the rectangular coordinate system, the rectangular or Cartesian is x comma y, right? Well, the polar coordinate is r comma theta. Okay, so r stands for a particular thing. It stands for the directed distance that you are from the origin. All right, we call it a fixed point of the pole, but you really just think of it as the origin. So r represents the distance that the point is from the origin. And then theta is basically going to represent what quadrant we're dealing with. Are we in the first quadrant? Are we in the second quadrant? Are we in the third or fourth quadrant? So to give you just a quick idea, this would be, say, r equals 1. So that's a circle with a radius of 1, right? This would be r equals 2. This would be r equals 3. So anywhere, if I graphed this point right here, I would be 3 units away from r, right? I would be, not r, I would be 3 units away from the origin. Okay, so that would be 3 units away from the origin. The other piece that goes with these polar coordinates is the theta piece. So let's say that our angle measure from 0 degrees, from the positive x-axis, let's say that our angle measure was represented by 30 degrees, or pi over 6. We always deal with radians in calculus, but you could think of it in terms of degrees if you wanted to. This line will continue over here too. We'll talk about what that is in a second. But first, let's go back to this blue point. So we've got this point that has an r value of 3, because we know it's 3 units away from the origin, and it's got a theta value of 30 degrees, or of pi over 6. So we would name this point the point 3, comma, 30 degrees. That's the polar coordinate system. All right, what if we were in the second quadrant over here? I don't know, let's say that it was 150 degrees. Say that this was the 150 degree line, because of course this is 90 degrees, this is 180, right? So 150 would be here. That would extend over there too. Again, we'll talk about that in a second. But if I named this point here, this point would be called 2, because it's 2 r's, or 2 units away from the origin, comma, 150 degrees. What about this point down here? All right. Well, what about this point right here? What would this point right here be? This would be an r value of 3 and 180 degrees, or pi if we were in radians. All right, let's go to this point here, all right, because this was the 30-degree line, right? Remember, we had the 30-degree line here. So this is also going to kind of be a 30-degree reference angle. You could think about it like that. So this would be the 210-degree line, right? So this is 30 degrees away from 180. All right, I've got a 30-degree reference angle here, a 30-degree reference angle here. So this would be 210 degrees. This point would be the point 3, because it's 3 r's, or 3 radii away from the origin. And the theta value would be 210 degrees. Okay. Now the only tricky thing that doesn't really come up in calculus, but r, if you go back to the definition of r, it represents the directed distance. All right. The directed distance means that if r is positive, you go directly towards your angle. So r is 3 in this case, so I go from the origin directly out 3 r values, and I plot the point at r equals 3, and the theta line is 210 degrees. The only tricky thing is that this point could also be named the point 3. Now let's name it negative 3, comma, 30 degrees. Right? This point right here could also be named the point negative 3, comma, 30 degrees. Why is that? Well, instead of going towards the 30-degree line 3 units out, I would go away from the 30-degree line, right? The polar opposite, not towards the 30-degree line, but away from the 30-degree line. And I'm at the 30-degree reference angle, right? So I'm at this point 3 comma 210 degrees, which is also written negative 3 comma 30 degrees. All right, let's just do one more over here again. This was 150 degrees, so if I go into the fourth quadrant here, this is going to be 330 degrees, right? It's a 30-degree reference angle in the second quadrant, so it's going to be the same thing in the fourth quadrant. And this point here could be named 2 comma 330 degrees, right? This point could also be named negative 2 comma 150 degrees, right? Because I'm going to go not towards the 150 degree line, but away from the 150 degree line to R values. All right, so that's a basic idea of polar coordinates. Let's talk about conversion formulas. All right, we can convert from rectangular, so if we had an X and a Y, we could go from rectangular to polar using these two formulas. All right, so watch. To get my R value, I'm going to do plus or minus the square root of 3 squared plus 4 squared, which is R equals plus or minus the square root of 25, or R equals plus or minus 5. Is it positive or is it negative? We'll talk about that in 1 second. I just went over that on the previous screen, but we'll talk about it in 1 second. Let's go to find theta. Here's how I find theta by using this formula. The tangent of theta equals, well, my y coordinate is 4 and my x coordinate is 3. So if on my calculator I do second tan, right, to get inverse tan, and then I type in 4 divided by 3, and it's going to tell me that my theta value is about 53 degrees. Okay, so my polar coordinate is going to be the point 5 comma 53 degrees. Now, why is it a positive 5? Well, let's come back here to the xy coordinate. All right, where is this point on the xy coordinate? Well, it's over 3 units and up 4 units, right? So that coordinate is in quadrant number 1. Where's 53 degrees? Well, that is in quadrant number 1, right? This would be the 53-degree line, and then this would be out 5 units. Does that make sense that it would be 5 units from the origin? Yeah, I think it would, and I'll tell you why. Because if I go over 3 and up 4, I could find the value of that R. It's the same thing as the hypotenuse, right? If I go over 3 and up 4, I could do 3 squared plus 4 squared equals 5 squared. So R kind of represents the hypotenuse of a right triangle. Right, the other conversion formula that you're going to want to know is converting from polar back to rectangular. This is much, much more important for calculus. You absolutely have to remember these formulas for calculus. All right, so to get an x value, you're going to take r and multiply it by the cosine of theta. Remember, you're going to have r and theta given to you. To find the y coordinate, you're going to take r and multiply it by the sine of theta. Here's how I remember these formulas, right? If I just solve this for the cosine, watch. If I solved this for the cosine, I would divide both sides by r. All right? What is the cosine equal? When you first learned trig, remember SOHCAHTOA, what was the cosine? Cosine was adjacent over hypotenuse, right? Well, that's what this is. This is the adjacent piece over the hypotenuse piece. Watch. All right, here's your angle measure. Here's theta. All right, what's the adjacent piece? Well, it's some x value. What's the hypotenuse piece? It's some r value, right? So the cosine of this angle is adjacent over hypotenuse. So that's how I remember that x equals r times the cosine of theta. X is going to go with the cosine of theta. Y goes with the sine of theta, because if I solved this for the sine of theta, I'd have the sine of theta equals y over r. If you just go back to this diagram here, All right, what's the sine of theta? Well, it's opposite. This would be some y value, wouldn't it be? So it's opposite over hypotenuse. That's the sine of this angle. All right, opposites over hypotenuse, y over r. So y goes with the sine. All right, so you have to remember these two formulas. X equals r cosine theta, y equals r sine theta. All right, we could figure out what the x coordinate is by doing 3 times the cosine of 30 degrees, which is 3 times radical 3 over 2. And we could figure out what the y coordinate is by doing 3 times the sine of 30 degrees, which is 3 times 1/2. Okay, so there's your, it's not pretty, but here's your x, y coordinate. All right, and that's what it looks like in polar form. All right, just a little bit more review of polar. I just want to show you how to sketch the graph of a polar equation. So say we have the equation r equals the sine of theta, and we wanted to sketch this graph. Here's what I would do. I would make a theta, comma, r table, and I would start to pick values for theta. All right, and I would plug them in and get the r value, and then I'd be able to sketch the graph. All right, so here's my polar graph. This is 0 degrees, 90 degrees, 180 degrees, 270, and then we're back to 360 over here. All right, so let's do this in blue. So if I plug 0 in for theta, the sine of 0 is 0. So that's where I start, right? If I plug 30 degrees in, the sine of 30 degrees is 1/2. Okay, so before I do that, let me just get some r values here. Say that this is r equals 1. And, oh, that's pretty bad. Let's do this here. That's r equals 1. That's r equals 2, and that'll be good enough. Okay, so if we go to the 30-degree line, think about where the 30-degree line is, and we go out 1/2 a unit. Okay, so that's the point 30 degrees and 1/2 for r. It's actually technically the point 1/2 comma 30 degrees because it's written r comma theta, but whatever. All right, so how about 60 degrees? What's the sine of 60 degrees? Well, that's radical 3 over 2, which is approximately 0.8770, I think. So let's go to the 60-degree line. Here's probably the 60-degree line. And let's go about 0.8 of an r, 0.8770 of an r. All right, so this is what my polar curve is starting to look like. What's the sine of 90 degrees? The sine of 90 degrees is 1. So let's go to the 90-degree line. Here it is. And let's go up 1 r value. Okay, so that's part of the graph of r equals the sine of theta. Let's keep going. 120 degrees. The sine of 120 degrees is radical 3 over 2, or 0.8770. All right, so that's going to be out here, right, because this is the 120-degree line probably. So I'm graphing this guy. 150 degrees, the sine of 150 degrees is 1/2. It's a 30-degree reference angle in quadrant 2. So here's my 150-degree line, and I'm out 1/2 a unit. So I'm there, and then 180 degrees, the sine of 180 degrees is 0. So I'm back where I started. Can we keep going? What's 210 degrees? We don't have to keep going because we're done, but watch, what's 210 degrees? Well, here's 210 degrees. Here's the 210-degree line. All right, and the sine of 210 degrees is a negative 1/2, right? It's a 30-degree reference angle in quadrant 3. So the sine of 30 degrees is 1/2, but since it's in quadrant 3, it's negative. So we go to this 210 line, here it is, and we go away from the 210 line 1/2 a unit. So we're actually back here, and now we're at this point retracing it. So what's going to happen is we're going to retrace that circle again, and r equals the sine of theta is going to be a circle, in quadrants 1 and 2. Let me show you that on my graphing calculator if I could. All right, so my graphing calculator, I've already got it in polar mode. I've played around with the window a little bit too. I went from 0 to 2 pi, which is standard, and I'm going from -2 to 2 on the x and y max and mins. Okay, so I go to y equals, I've got r equals the sine of theta. Let me just show you. I'm hitting this button right here, and then that button right there for the sine of theta. Close the parentheses, hit enter, hit graph, and there you go. You've got a circle in quadrants 1 and 2. Now watch this. If I go back to my window and instead of doing 2 pi, I go 0 to pi, I would still get the exact same graph. All right, that's important to know the bounds. What if I went 0 to not quite pi? What if I went to like 2.8? What would happen? Well, it wouldn't quite finish the graph. Can you see that? Let me go to maybe 2.65. Right, it's not going to quite finish the graph, so it's not going to close. But the bounds of this polar curve is going to be from 0 to pi, right? That's going to get the entire curve. If I go 0 to 2 pi, I'm just going to be retracing the curve. If I go 0 to, I don't know, 10 pi, I would just continue to retrace the curve. Watch, this means up here that the curve is still working, so it just keeps retracing the curve. So it's important in calculus to know the bounds of these graphs. So you kind of need to know a little bit about how to graph polar equations to figure out sometimes what the bounds are. Let's just take a look at another one on the graphing calculator. So if I go back to my grapher and I do, so sometimes on these polar equations they're going to let you use a graphing calculator. Other times they won't. So if I type in 4 cosine theta, whoops, that's not going to work. 4 cosine theta, close the brackets, hit enter. All right, and if I graph it, now obviously my window's a little messed up, but this is going to be a circle in quadrants 1 and 4 because the cosine is positive in quadrants 1 and 4. All right, so let's go back to our standard 2 pi, and let's go to our standard -10 to 10. All right, and when we graph it, there you go. It's a circle in quadrants 1 and 4. Now, again, you can play around with the window. Does this get graphed from 0 to pi? I don't know. Let's see. From 0 to pi, we've got the entire graph. What if we went from 0? Maybe it gets graphed from 0 to pi divided by 2. What do you think about that? No, you're only going to get half the graph. All right, so from 0 to pi is going to give you that full polar graph for r equals 4 cosine theta. All right, so depending upon the curve that you have, it all depends upon how many degrees or how many radians you need to graph the curve. So these first two, r equals the sine of theta and r equals 4 cosine theta, require us to go pi units or 180 degrees to graph the curve. All right, so that's what it looks like. All right, so let's get to the calculus end of things. To find a derivative of a polar equation, you're going to have to remember these conversion formulas. X equals r cosine theta, y equals r sine theta. And then to get the derivative, to get dy over dx, you're going to take the derivative of the y equation. Right, here's the y equation. What's its derivative? Well, it's the product rule. It's the first times the derivative of the second plus the second, here's the second, times the derivative of the first. Okay, so that's my derivative of the y, and then my derivative of the x, which is going to be in the bottom part of the fraction, is the same thing. It's the first times the derivative of the second plus the second times the derivative of the first. All right, so that's how you're going to come up with dy over dx. It's the derivative of the y conversion formula, y equals r times sine theta, over the derivative of the x conversion formula, x equals r cosine theta. All right, so that's how you're going to come up with the derivative formula for a polar curve. That's how you're going to find the slope of a polar curve. All right, so let's do an example. Find the derivative of r equals 4 cosine theta at theta equals pi over 6. Okay, so I've got my conversion formulas. All right, so my dy over dx is going to equal the derivative of the y equation, which is the first, times the derivative of the second, plus the second, times the derivative of the first, over the derivative of the x equation. The first times the derivative of the second, plus the second times the derivative of the first. Okay, and then we're going to substitute. We're going to take r, which is 4 cosine theta, and we're going to plug it in. And then we're going to need r prime. All right, so let's figure out right now what the derivative of r is. What's the derivative of r? Well, it's negative 4 sine theta, all right? All right, so when I come to my dy over dx, I get r, which is 4 cosine theta, times the cosine theta, plus the sine of theta times r prime, which is negative 4 sine theta, all over r, which is 4 cosine theta, times negative sine of theta, plus the cosine of theta times r prime, negative 4 sine theta. All right, and then they want me to evaluate this derivative at theta equals pi over 6. Okay, so at theta equals 30 degrees. All right, so let's plug those values in here. So let's see here. What's the cosine of 30 degrees? Well, it's radical 3 over 2. What's the cosine of 30 degrees? Radical 3 over 2. Plus, what's the sine of 30 degrees? 1/2 times the negative 4 times the sine of 30 degrees, 1/2. All over 4 times the cosine of 30 degrees, radical 3 over 2, times the negative sine of 30 degrees is going to be negative 1/2, plus the cosine of 30 degrees is radical 3 over 2, and the sine of 30 degrees is 1/2. All right, so let's see if we could simplify this. Dy over dx equals, those will cancel. It looks like we get a 3 plus negative 2 times a 1/2 is going to be a negative 1. All right, I hope that's right. And here those will cancel, so I'm going to get a negative radical 3 plus, looks like another negative radical 3, right? So it looks like I have 2 over negative 2 radical 3, or negative 1 over radical 3, or negative radical 3 over 3 if you want to rationalize it, but I'm going to stick with that. All right, so that's the slope of r equals 4 cosine theta at theta equals pi over 6. Now I think, if I plan this correctly, I have r equals 4 cosine theta in my calculator, all right? So if I graph it and then I do second trace number 2, all right, that's going to give me the derivative, and I want that derivative at pi divided by 6. And it tells me that it's negative 0.5773. Let's see, what is 1 divided by, what is 1 divided by the square root of 3? 0.5773, right? So negative 1 over radical 3 is approximately negative 0.577, whatever it was. All right, so I can get that on the calculator. Let's get this out of here. Get that on the calculator as well. I didn't put the negative in there, right? It was really negative 1 divided by the square root of 3. All right, so that's the same thing as what I get when I graph. I do second trace number 2 for the derivative, and I evaluate that at pi divided by 6. All right, so I get the same thing. All right, so that's finding the derivative of a polar equation. Let's talk about finding the area of a polar curve. That's going to be a formula. That is going to be the integral of 1/2 r squared d theta. All right, so if I want to find the area enclosed by this graph, r equals 4 plus 4 sine theta, that area is going to be the integral of 1/2 times 4 plus 4 sine theta, the quantity squared, d theta, right? Now, the tough part is always these bounds. You know, what is the theta value and what is the theta value here for the bounds? So you've got to go either to the graphing calculator or graph it by hand, and you got to figure out what the bounds are. You got to figure out how long it takes us to graph this curve. So 4 plus 4 sine theta. What do you think? That's actually not the curve graphed you may think it is, but if I go to my window, and if I just default to 0 to 2 pi, a lot of times that's the best way to go, and I graph it again, you can see that it's got a bottom to it, right? This is a cardioid. See how they try to kind of tip you off on that a little bit? Find the area of the cardioid. So this kind of looks like an upside down heart, right? So if I wanted the area of that, I would integrate this from 0 up to 2 pi. Why 0 up to 2 pi? Well, because that's how long it takes me to graph the entire curve. If I went to like 5.7, oops, if I went to 5.7, you know, I wouldn't quite finish the curve. All right, so I got to go all the way to 2 pi to get that curve in. All right, so let's do this integral on the graphing calculator. The bummer is that, watch, when you do second trace, there's no integral for polar mode. So you have to go to mode, and you have to go back to function mode. And then you have to type in 0.5 times 4 plus 4 sine of theta, the variable, close the brackets twice and square it. All right, and then if I graph this now, it's not going to look anything like the polar equation. But if I integrate it, second trace number 7, my lower bound is 0, my upper bound is 2 pi. I should get the area of the curve, 75.398. 75.398. Remember, on the AP exam, round everything to 3 decimal places, okay? All right, so that's the area of a polar curve. Again, the tough part, I feel like, is figuring out what those bounds are. Remember, for the first 2 that we did, r equals sine theta. All right, here's r equals sine theta. That only took us 180 degrees to graph. All right, that second one, r equals 4 cosine theta, only took us 180 degrees to graph as well. But this one took us, whoops, not this one. This one took us 360 degrees. All right, and then one more quick thing, if you can hang in there with me, the area between 2 polar curves is going to be this formula. All right, where you're going to integrate 1/2 times the top curve squared minus the bottom curve squared. All right, so that's the formula that we're going to use, and we'll rewrite that formula here. All right, so the area is going to be the integral of 1/2 your top curve or your right curve, whatever your r value is squared, minus your bottom curve squared, d theta. All right, so that's just this formula written a tiny bit differently, but make sure you don't square them on the outside of the parentheses. All right, the square does not go here. You square the individual equations. All right, and then subtract them. All right, so if we wanted to just very quickly figure out what this looked like, let's go back to mode. Let's go to polar. Let's go to r equals. And what are we looking for here? R equals 6, which is going to be the 6th circle. And then 3 cosecant is going to be 3 divided by the sine. All right, so if I graphed that, that's what that looks like. All right, so r equals 6 is obviously the circle, and 3 cosecant theta is actually a horizontal line that's equivalent to y equals 3. All right, so graphically, just so we can get a picture of what's going on here, this is r equals 6, and this is r equals 3 cosecant. All right, what's the bottom line here? Well, the bottom line here is we need those bounds. But before we do the bounds, let's write the integral. 1/2 times, what's the top curve? Well, the top curve is the red curve. All right, the top curve is 6. So 6 squared minus, what's the bottom curve? The bottom curve is 3 cosecant theta squared. All right, d theta. All right, now I need the bounds of integration. How do I find the bounds of integration? Well, I need the points of intersection. All right, so I've got to take 3 cosecant theta, and I've got to set it equal to 6. I've got to figure out where these guys intersect each other. All right, so if I solve this equation, dividing by 3, I get that. Remember, the cosecant is the reciprocal of the sine, and the sine of 30 degrees, or pi over 6, and 150 degrees, or 5 pi over 6, is where the sine equals 1/2. So these are going to be my bounds, pi over 6 and 5 pi over 6. Okay, so here's my integral to find the area bounded by these two curves, right? Inside r equals 6 and above r equals 3 cosecant theta. All right, so if I plug that into the graphing calculator, I would get my answer. Let me try to do that real quickly here. So I'm going to go back to mode. I've got to go down to function because there's no way for me to integrate inside polar mode. So I'm going to do 0.5 times 36 minus, now this is going to be tough. I got to open up my brackets and do 3 divided by the sine. All right, close that twice and square it. Let me just make sure I'm doing this right. So I've got 0.5, and then I opened up the parentheses, and I've got 6 squared minus, and then all of this stuff squared, and I should be good to go. All right, so I graph it again. That's not going to look like the polar graph, but I do second trace number 7, and I'm going to integrate from pi divided by 6 to 5 pi divided by 6. And 22.111. All right, so this is going to be 22.111 is going to represent the area bounded by those two curves. All right, that's it. Thanks for watching.